طيب, Bismillah ar-Rahman ar-Rahim. So I prepared some exercises to go through. If you have specific questions in addition to that, I'll be glad to go through it. So the exercises summarize chapter 4, 5, and 11. So for chapter 4 first, we discussed the digital transmission. So to transfer digital data using a digital signal. Okay. So this is baseband transmission. So in this chapter, we discussed line coding schemes. We discussed the pros and cons for each line coding scheme and so on. So the first exercise here talks about how to draw the signal using specific line coding scheme, which is 2B1Q. For 2B1Q, we know that we have how many bits? 2, and we have how many signal levels? 4. Okay, so 2 to the power m is exactly equal to the number of signal levels. طيب, so here we are required to draw the digital signal for these 4 cases. For the first case, we have straight zeros, and then we have different streams for each case. So the best thing is first, especially for 2B1Q, is to write the lookup table. Okay, so we have 4 different combinations of bits. We have 0, 0, 0, 1, 1, 0, and 1, 1. Then the signal levels, you can use whatever signal level for each bit combination. It doesn't matter. So here we can use +1, +3, -1, -3. Okay, but remember in 2B1Q we had 2 cases. One case where the previous level is positive, and the other one is when the previous level is negative. When the previous level is negative, we just have to invert everything. So +1 becomes -1. So for this you don't have a choice. You have to invert. So -3 + 1 + 3. Okay? So this is 80% of the grade. خلاص, once you put it this way, the rest is really systematic. So for straight zeros, for the first one, 0, 0, 0, 0 is +1. And since the level is positive, we always have to look at this column. So it's always a +1, and it remains like that forever, for all the bits. Okay, so there's no change. Okay. Then for the case of all ones, the 1, 1 is -3. So the first one is -3. And then since this level is negative, we have to look at the second column now. Okay? So 1, 1 becomes +3. Hey, 1, 1 in the second column becomes +3. So this becomes a +3. And now we are positive, then we have to go negative. Okay. Sorry, now we are positive, we have to look at the first column, when the previous level is positive. So it goes to -3, and then it goes to +3, and then -3, and then +3, and then -3, and then +3. So, okay. And that's what we said. This inversion allows me to, for the case of straight ones, at least, we can perform some alternation, which means that this alternation will enhance error detection and the self-synchronization. Okay? So this second column, that's what it's used for. For the third case, we have 0, 1. For 0, 1, 0, 1 here is positive. 0, 1 is +3, so it becomes like this. And since it's positive, we will remain in the first column, so it becomes positive, 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 and so on. Okay. Then it's 0, 0, 1, 1, and so on. So for 0, 0, we have to go +1. Okay. then 1 1. 1 1 is minus 3. So we have to go minus 3. So once we go to minus, then we have to go to the second column. Okay? Then 0 0 becomes minus 1. And we're still in minus. Okay? Then 1 1 becomes 3 in that case. Right? And now we are positive, so we look here. 0 0 becomes 1. And then 1 1 becomes minus 3. And then negative 1. And then 3. So it's like a periodic signal, but each period looks a little bit funny. Okay? So these are the 4 cases. So the other part of the question is tricky بقى. It's not exactly what we have studied in class. For this graphs, guess the bandwidth for this scheme, for the 2B1Q, based on the number of changes in these signals. Okay? What we have started in class is the statistical average bandwidth based on C, which is normally we take it as half, and R, which is the number of bits elements divided by the number of signal elements, right? And for this 2B1Q, it's easy. R is 2, right? So the number of signal elements here is 1 for each 2 bits. So R is 2, which means that the the statistical average baud rate, okay, is based on C. C is half on average, times N times 1 over R, and R is 2, so it becomes N over 4. This is the statistical average, okay, based on the value of C. But that's not what the question asks for. What the question asks for is to try to calculate the same bandwidth, but using the number of changes in the current signals only. So we have 4 signals. Okay? So it's like you need to go back to the definition of the baud rate. The baud rate is actually is defined as what? The number of changes per unit time. Okay? So we need to calculate the average number of changes given these 4 signals. Okay? So, sorry. It becomes funny a little bit. Okay, so for these 4 signals, number of changes in terms of average, يعني, equals what? How many changes in this signal? 0. What is this, the second one? لا, the second one اللي هي اللي تحت هنا. Okay? لا, هي 7 بس. 1, 2, 3, 4, 5, 6, 7. 7. Plus the third one is 0. Plus the fourth one is A. Sorry?
8 changes.
لا هم 8 for هم 8 bit patterns, right? هو if you count the previous bit, then it's 8, yes. عموما يعني لو كتبتها 7 او 8, it doesn't matter.
But you don't usually count the previous bit.
لا, you don't assume what was before. يعني I did not tell you what the signal level was before. I did not tell you that. So you don't know whether there was a change or not. And you don't know what's after that. Yes, if the previous is positive, then there is a change and it becomes 8, then it's fine. يعني ما فيش مشكلة. ماشي, that's fine. 7 or 8, it doesn't really matter. But see, if I give you the previous signal level, عموما. طيب. So these are the number of changes for each case. So the average is that we have to get the average for these 4 signals. Okay? طيب. But this is the average number of changes for how many bits?
And 2 bits,
16 bits. Okay? So the average overall is to divide by 16. So this is the average number of changes per bit. Okay? Okay? So multiply that by any value of n. خلاص. So this becomes the number of changes or the average baud rate. But this is based on these 4 signals only. Okay? So that's, يعني statistical average is coming from what? يعني this original equation is coming from what? It's coming from the fact that you try all possible combinations. Okay? Infinite number of combinations. And then you calculate the value of C based on that. And then you multiply C by n and by 1 over r and you get the... So this is the average baud rate but based on these 4 signals only. Okay? So that's what the question asks for because this calculates the average number of changes for this 16 bits. So the average number of changes per bit is to divide by 16. And then multiply by any n. أيوه.
بس هو هنا قال بير بت ولا بس number of changes؟
لا هو هنا بيقول لك calculate the baud rate based on the number of changes in these segments. That's it.
ما احنا نقول divide by 16.
ما هو if you don't divide by 16 then the number of changes that you are calculating is the number of changes per 16 bits. Okay? For each 16 bits, for these 4 signals, that's the number of changes that you have. Okay? طيب, for any arbitrary n بقى, يعني for any arbitrary n such that n is the number of bits بقى. يعني هنا الكيس ديت كانت for 16 bits only. Okay? So for 16 bits, that's the average number of changes that you get. So for any value of n, we divide by 16 and multiply by n. خلاص. It's like we get it for each bit, and then we multiply by the number of bits. Then whatever by n is, we can give you the average number of changes. But again, this is based on these 4 signals only, not statistical average. That's what the question is asking for. Okay?
This is the answer for this question.
Yeah, this is the answer for this question because the question is asking for calculating the average baud rate based on the average number of changes in these signals, in these 4 signals. Okay? If I don't give you these 4 signals, then I need you only to calculate R and I give you C. So you calculate the statistical average. That's what we have studied in class. طيب, the exercise number 2, what is the result of scrambling the sequence 1, 1, 1 and all zeros using one of the following scrambling techniques? If we go back to scrambling, remember, scrambling, what is the main purpose of scrambling was to enhance synchronization and error detection, right? Enhance the synchronization error detection. What is the other alternative that does the exact same thing? Block coding, yes, block coding. But what was the problem for block coding, Ken? Overhead, because we have to map each 4 bits into 5 bits, or 8 bits into 10 bits. So it adds overhead, okay? And we said that this overhead is required to enhance the error control and the self-synchronization. That's good. So scrambling tries to achieve the exact same thing, but even without the overhead, okay? And it tries to do that by substituting a consecutive number of zeros, okay? Because for AMI اللي هو alternate mark invert, the AMI sequence is attractive, but the problem is the 0 is mapped as 0 voltage level all the time. Okay, so if you have consecutive zeros like this, you have straight 0 voltage level. But the 1 is mapped as bipolar. So 1 time negative, 1 time positive, 1 time negative, and 1. So for straight ones, it's good. But for straight zeros, it was bad because the signal level is always 0, and that was bad. So scrambling tries to compensate for this by substituting consecutive number of zeros using certain sequence. But the issue here is that we are trying to do this scrambling in such a way that, on one hand, introduce more changes in the signal, but on the other hand, make the receiver able to distinguish that this is not the proper sequence of AMI. Okay? Yani the receiver needs to distinguish that this is not the proper sequence of AMI, this is actually scrambling. AMI with scrambling. Okay? So we achieve that by introducing the concept of violate. فاكرين؟ we have to introduce the concept of violate. So for B8ZS, on each 8 consecutive zeros are mapped into حد فكر 0 0 0 VB 0 VB. Okay. So for case A, the bits 1 1 1 and all zeros. The first one here is mapped either positive or negative. Based on what? Based on the one before it. If the one before it was positive, then it's negative. If the one before it was negative, it's positive. So the last non-zero signal level has been positive. So this one is negative. A negative -1 or negative -3 or negative -2 مش هتفرق أي حاجة. أي negative. لأن هو أصلا AMI uses only 2 signal levels. Or 3 يعني given the 0 signal level. So this one is negative, and then the other one is positive, and the other one is negative. Until now, this is the proper sequence of AMI. I did not change anything. Okay? And now we have 8 zeros. We have how many? We have 8 zeros and again another 3 zeros. So these 8 zeros are going to have to be substituted by this sequence. Okay? So now we need to perform the scrambling. So the 8 zeros becomes a violate. So the first one, 0 0 0 first, 0 0 0. Okay, so the first are 3 zeros, and then violate. Violate means that it's equal to this, so that the receiver would know that this is not bipolar. It's not the proper sequence of AMI. So this is V. And then after V we have bipolar, and then we have 0. This one, and then we have violate again. Okay? And then we have bipolar, and then that's it. So we finish substituting the 8 zeros. So now we have another 3 consecutive zeros. What do we do with those? Just normal. خلاص, we go back to the normal sequence, because they are not 8 consecutive zeros. So we don't have to do any substitution in that case. واضح? طيب, for the second case, the HD B3, it tries to be more conservative, as we said before. And in that case, the substitution works as follows. We have 0 0 0 V for each 4 zeros we substitute by V. And this is for the case when the number of ones before, or the number of non-zero signal elements, is odd. And it becomes B00V when it's even. Okay? So again, it's -1 and then 1 and then -1, so that's the same. And then we do by the scrambling. For the scrambling, I'm telling you here that the number of non-zero pulses, including the triple ones, including those triple ones, يعني, the total number is odd, which means that we take this substitution. Okay? So it becomes 0 0 0 and then V. صح? This is V. Okay? And then we have another 4 zeros. What is the number of non-zero pulses here? Is 0. Okay? So between these 4 zeros and the other 4 zeros, we have 0 number of non-zero pulses, or in other words, 0 number of ones. Okay? So we go to this substitution. So it becomes B, and then 0, and then 0, and then V. Okay? And then the 0 ones, those are not 4 consecutive ones. So it becomes 0 0 0. So here we substitute each 4 consecutive ones, okay, not 3. سهلة? Okay, so that's for the digital transmission for chapter 4. For chapter 5, we talked about analog transmission. We said that for analog transmission, we need to transmit digital bits, but in that case, using digital signal, but it's still in the baseband. Okay? So the main equation that we have studied here is that the bandwidth or the baud rate equals 1 plus D times S, where S is N times 1 over R. This IQ diagram, so that's the main equation that we have studied. So here we are required to draw the constellation diagram. For the constellation diagram, or IQ diagram, for these following cases. The first case is ASK with peak amplitude values of 1 and 3. For ASK, as we have started, we don't change the phase, which means that the phase of the sine wave, the analog signal that is used to represent the digital data, is always 0. Okay? So for the IQ diagram, the phase is always 0, which means that we are always in the x-axis. Okay? And we only need to represent the amplitude in that case. So one amplitude is 1 and one amplitude is 3, which means that we will represent the 0 as a sine wave with amplitude 1, which means here, and the 1 as a sine wave of amplitude 3. So it's only 2 dots, that's it. Okay? So in terms of IQ diagram, the ASK with this specification is only 2 dots. These 2 dots represent 2 symbols. One symbol represents a 0, one symbol represents a 1. Easy. Okay? Type. For case B, we have Bpsk, binary phase shift keying. So again, we have 2 symbols to represent 1 bit, 0 or 1. Okay? But this time, we will change the phase, but not the amplitude. For Bpsk, that's what we do. We change the phase, but not the amplitude. So, so here the amplitude is only 2, and I didn't have to give you the other amplitude, right? Because it's the same. It's just with a phase shift of 180 degrees. So whether you started from here, whether you do it this way or you do it this way, it doesn't matter. The main thing is that either or, طبعا, not both. So the main thing is that the phase difference is always 180 degrees because we have only 2 symbols. ماشي? So this is 2, and this is -2. Type. For the case C, we have Qpsk. In that case, for Qpsk, we have 2 bits and 4 different symbols. Okay? The phase difference between these 4 symbols has to be 90 degrees. So, again, if you want to do it this way, that's fine. Remember, the amplitude is 3, so this is 3. So the amplitude is always from the origin. Or another way of doing this is by using the 45 degrees. So in that case, this is 3. Okay? This is 3, which means, what is this? This is the 3 divided by square root of 2. So it's not 3. Huh? Remember, so the amplitude is always from 0, from the origin. So this is for Qpsk. So we have 4 symbols, and that's how it looks like. Type. For the case of 8 QAM, for QAM, it's quadrature amplitude modulation. We change both the amplitude and the phase. Okay? So 8 QAM can be represented as 2 Qpsk, such that each Qpsk has 4 symbols with the same amplitude. Okay? So it's like this. So we can put it as this is 1 and this is 3. Those are the two amplitudes. And for this one, we have to use 4 symbols like. And this one, we have to use 4 symbols like this. Okay? Or you can rotate 45 degrees and make it from the x-axis and the y-axis. Both are fine, as long as this phase difference is 90 degrees. That's the main constraint. Any questions? واضح? Straightforward. Okay. A quick question here. Why do we use QAM over PSK? Why? So does that make the analog transmission more bandwidth efficient? سؤال فلسفي بقى. Less bandwidth efficient?
Because you're making smaller squares, I think. Because you're making smaller areas, basically.
هو أنت عايز تقول إن هو يعني if I use only PSK and I use مثلا يعني let's say we are trying to use 8 PSK here. Okay? How can I represent 8 PSK? 8 PSK, not 8 QAM.
You have 4 dots in each quarter.
No. لا. Yeah, this is 16 QAM. So يعني ايه الفرق بين what is the difference between 8 PSK and 8 QAM? 8 QAM, I have extra degree of freedom to change the amplitude. 8 PSK, I cannot change the amplitude.
8 PSK have 8 different phases?
Yes, 8 different dots that form a circle like this. Okay, such that the amplitude is the same. So it's a circle. I cannot change the amplitude. Okay? The question now is, what is the difference between this and this?
Because of the amplitude, if we need more points, you're probably going to need a larger voltage. So you have more differences between them.
More differences? لا, I don't have any difference in terms of voltage level at all.
The error can happen in 8 PSK more than QAM?
Why?
Because the difference is very small.
Yes, the distance here squeezed. The difference is close. So by introducing noise, this symbol can easily go close to this symbol and it becomes undistinguishable by the receiver. But if QAM, what QAM does? What QAM does is actually it provides more degrees of freedom to change the amplitude, so it makes you more able to distribute the symbols on the IQ diagram more efficiently, so that the distance between the symbols becomes further away. Because if you change the phase only, this makes all the symbols within a circle and the distance start to get closer and closer. But if you have another degree of freedom to change the amplitude and the phase, this gives you more flexibility to make the distance between the symbols further, in which case, what is the effect of this? Probability of error will be lower in that case. It will be better in terms of probability of error.
More bandwidth?
No, not more bandwidth. It's the same bandwidth. Bandwidth is only based on what? 1 plus d times n times 1 over r. R is the same for all cases, regardless of whether it might be affected a little. D might be affected a little bit, but not that much. Okay? And if we use the same D for both, then it's the same bandwidth. But the probability of error is different. Probability of error is much better in the case of QAM. And that's why QAM is more commonly used in digital communication. But not the bandwidth. The bandwidth is the same. ماشي? Using this IQ diagram, we need to have 1024 dots here. And you can arrange them in any way, it doesn't matter. You can arrange them using different circles of QPSK, different circles of APSK, whatever you want. Because this will not affect the bandwidth. It does affect the probability of error, but it doesn't affect the bandwidth. So that's for this exercise. So that actually helps for this example. So here, a corporation has a medium with a 1 megahertz bandwidth as low path. So this company has 1 megahertz bandwidth, and it wants to divide this into 10 separate independent channels. So it wants to divide this into 10 different channels, such that each channel should be able to carry 1 megabits per second signal using analog transmission. Okay? Okay, so that can happen using any of the techniques that we talked about. ASK, PSK, whatever. FSK, anything. So here we are using QAM. If I change this to PSK, will that make any difference? Will it? If we're talking about bandwidth, then it doesn't make any difference. That's why we said in the example before, if we're talking about bandwidth, then it doesn't make any difference. If we're talking about probability of error, then it does make a difference. Okay? But luckily, in class, we did not learn how to calculate the probability of error because it's quite complicated. The probability of error for QAM is quite complicated. Okay? But in terms of bandwidth, they are the same. And we know that the bandwidth equals to 1 plus d times n times 1 over r. So what is the minimum number of bits per baud? What is this? This is r. Okay? Yani, how many bits can be represented by one symbol? Okay? So that's r, basically. So what is the number of points in the constellation diagram? So let's see. So we know that the bandwidth equals to 1 plus d. What is the bandwidth of a channel? What is the bandwidth of the channel?
100 kilohertz. Or 100 kilohertz.
100 kilohertz will get me in. So remember, we have 1 megahertz, but this is divided into 10 different channels. So bandwidth per channel equals to 1 megahertz divided by 10 channels, which is 1 kilohertz. 100 kilohertz. So 100 kilohertz. This is the bandwidth for one channel. This bandwidth equals to 1 plus d times n times 1 over r. So what's r? R equals 100 times 10 to the power 3. And r is actually n divided by that. So n is 10 to the power 6 divided by this. صح كده? So this becomes a 10 بس. What is the unit? No unit. No unit. Bits per baud يعني اللي هو يعني bits per baud ماشي. This is the number of bits per baud, or the ratio between the number of data elements and the number of signal elements. Okay? So the number of bits per baud is 10. What is about the number of constellation? Okay, so the number of constellation is actually by the number of symbols. It's 2 to the power 10, which is 1024. This means that we need 1024 QAM to represent the signal in each channel. 1024 QAM. Okay? Any questions here? يعني using بقى. Any questions? All right. So in the last chapter we talk about data link control. In data link control, we discussed two major topics. The first one is two major topics correspond to the two major functionalities of the data link control sublayer, which are framing and then flow and error control. For framing, we talked about bit stuffing and byte stuffing and so on, right? And then for the flow and error control, we talked about the different techniques for flow and error control, including stop and wait, go back in, and for the case when there is a channel error, for the case when the channel is perfect, and so on. Okay. So here we have a system that uses stop and wait ARQ, and I want you to read the question carefully, because if I don't put this, for example, the question becomes much simpler, and if you don't pay attention to this, you solve it as if it's ARQ, you complicate it for no reason, okay? So you lose grade, you don't actually get, you lose grade. So just by reading the question carefully, you can avoid losing some grades. But here, unfortunately, we have to deal with ARQ. So we do need to have that, which means that the channel is not perfect. The channel has some errors.
So is it possible that you can solve it with ARQ and without?
Yeah, we studied the two cases. We studied stop and wait when the channel is perfect, so we did not put the ARQ. And then when the channel is not perfect, this means that you can send some frames and they don't arrive to the other end. Or you can send some frames and the acknowledgement does not arrive back. So this is because of the channel errors. And in both cases, you have to retransmit. So here we have sender A. You have A. You have A and you have B, the receiver, okay? And then the bandwidth between them, or the thickness of the pipe, is 1 megabits per second. This is the bandwidth. If each packet, so A has a packet with a length of 1,000 bits, and the receiver is 5,000 kilometers away. Okay? And then the propagation speed is 2 times 10 to the power 8 meter per second. So from these four values, naturally we can calculate the two common the transmission delay and the propagation delay. So we can do that. This is for the second part of the question. For the first part, however, we are requested to fill the missing lines for the sender, for the sender to process an event. Okay? How many events does the sender need to handle? Two. Bravo عليك. The request to send and arrival notification from the receiver. For stop and wait, we need to accommodate acknowledgement. Why? Because the channel is not perfect. So I don't know if the frame is sent that it really arrived to the receiver. And the only way for me to guarantee that it arrived to the receiver is to wait for acknowledgement.
Time out to arrive. Time out.
Time out, yes, here, yes, there is time out as well, yes, صحيح. There is time out, yes. So it's three events, yes. Type. So here the question is asking for only request to send, which means that I want you to write the pseudocode for only this means I have good mood, so I can ask you for مثلا the three, but hopefully it will not be more than like one event.
Doctor, we are attending on the first time.
فأنت من اللي هم one event. Okay, so here we are required to write the pseudocode for the request to send. And remember we have ARQ here. طيب. So request to send is coming from which layer?
Upper layer.
From the upper layer, from the network layer, right? So the network layer is puts the packet into a buffer and then it fires the request to send event. So now the data link control sublayer needs to go to that buffer and get data. So the first thing is we got the data. Hell. So what do we do about with this data? So we have to first we have to make a frame out of this packet, right? So first make frame. All right. So make a frame. Remember that for ARQ we needed to use some sequence number. Why? Because when we send, if we have a timeout, we don't know whether the frame has arrived or the acknowledgement was lost. Okay? So when we retransmit, the receiver needs to know whether this is a duplicate packet or a new packet. And this is the only two states that I have. I don't have any other state. For the receiver, it's either a new packet or a duplicate packet. So in that case, I need to account for sequence number. So for each packet that I send, I need to store the sequence number in the packet so that the receiver would know whether this is a duplicate packet or a new packet, right? And that's why here we have, so remember these parameters are for you to use. They are not for you to just look at, okay? Now we made the frame. Make the frame includes about all the bit stuffing, byte stuffing, creating the header, everything. Okay, so now we have a frame, a formal frame. So now we can send it, but remember, because we have ARQ, we have to store, bravo. Why? Because if this frame is lost, we don't have a copy of it. Okay, so storing the frame before you send it is a consequence of this word. If we don't have this word, then life is very simple. Make frame, send frame. Make frame, send frame. That's it. I don't have to use any sequence number. I don't have to do anything. Okay? So just by this word, we have to account for all of this. Right. So now we can send the frame. Okay? Anything before that? لا خلاص, we can send the frame. Once we send the frame, purge happens when we receive the acknowledgement. That's not part of this event. It's not part of this event. So there are three things we need to do here. The first thing is that SN needs to be incremented. Once you send, you always have to increment the sequence number. But this is modulo A 2, which means it goes 0, 1, 0, 1, 0, 1. And we need only two sequence numbers. We don't need more than that. Okay? طيب, what else? Start timer, كويس. Start timer. SN, do we have to put SN here? Why? Why? Yeah, as we said, the only exception that we need to start a timer per frame is when? For? No. For selective repeat only. For selective repeat is the only case where we needed to start a timer per frame. Otherwise, زي ما قلنا, stop and wait is nothing but a special case of go back and when the window size is 1. Okay? So it's a window technique, but it's a special case where the window size is 1. So in both cases, the timer is 1 timer per window. ماشي? The last step here is just to, so if you notice this can send, we set it to true or false? False. Why? Because while you are waiting for the acknowledgement to come, if another event like this is fired, you cannot send. Which corresponds for the case of go back N, that the incoming frame is outside the window. Okay? So now this is what it means. Once I send a frame, the window has been consumed. خلاص, ما هو window size is 1. Right? So here, this exactly equivalent for the case of go back N, that I need to check whether the incoming frame has a sequence number which is outside the window. Okay? Here, because the window size is 1, so I only have two cases. Either the current or I cannot send anything because the window size is only one.
Is it possible if you put a wait function instead of putting it to false?
Wait function.
Wait function.
Wait for
لا لا هو for the case of هو ما فيش حاجة اسمها wait function. هو for the case of go back n, it's either inside the window. Inside the window, how do I check it? The sequence number is within the window. Okay? If the sequence number is outside the window, then I cannot send. I just sleep, go back to sleep again. I cannot do
When I
anything.
say wait, I mean sleep. You just
Yes, wait, yes. So wait معناها sleep خلاص. I go back and I wait for another event to come. Okay? So that's the sequence for the case of stop and wait. In go back n, there is slight modification. This can send becomes a window, and you have to check whether the incoming frame is outside the window. And of course, here the increment of Sn becomes a modulo. لا, it depends on the sequence numbers. Okay? Depends on the sequence number. And the sequence numbers is always more than the window size by at least one. صح? Okay? So if we have, for example, 16 different sequence numbers, the maximum window size is 15 in that case. Okay? So that's for the first part. Right. For the second part, we need to calculate two things. We need to calculate the propagation time. The propagation time is what? Is distance divided by speed. صح? Which is, the distance is 5,000 kilometers divided by the speed, which is 2 times 10 to the power 8. This is how much you can calculate. It's actually 50 divided by 2 milliseconds. Okay? Type the transmission time بقى is different. Transmission time is the length of the frame, which is 1,000 divided by the bandwidth. Right? So this is 1 millisecond. So keep these two values in mind. So the propagation delay is 25 milliseconds, and the transmission time is the number of the size, the frame size.
the length as well. I cannot see
Each bit carries.
Yeah.
If each packet carries.
okay.
Okay. Second. Any question?
What was 1,000? I'm looking.
1,000 is طيب, assuming that 20% of the frames or acknowledgement get lost. For the case of stop and wait, if the frame is lost or the acknowledgement is lost, does that make any difference for you? The reaction is the same. You have to retransmit in both cases. Okay. So how long does it take to send 1 million bits of data? I should here write ignore transmission time for acknowledgement. يعني this should be actually this should be put so that you don't get confused, because the transmission time is based on the length of the frame, right? So the original frame is 1,000 bits. What is the size of the acknowledgement? It's only a header, right? So this could be like 1 bit or 1 byte. Okay, so we can easily ignore the transmission time of that acknowledgement frame, because it does not contain any data. It's just like 1 byte. Type. So we need to transfer 1 million bits of data, a file which contains 1 million bits of data. So what is the number of frames we need to send with no errors, without errors?
1,000.
This is what we have: 1 million bits divided by the length of the frame, which is 1,000. That's but we have 1,000 frames, right? So تعال بقى نشوف بقى, يعني just see بقى the timeline of how we can send these 1,000 frames. This is A, okay, and this is B. For stop and wait, A has these 1,000 frames like this, And then what it does is that it takes the first one, frame 0 مثلا, and then it transfers frame 0. It transfers frame 0. So now it finished the transmission. This takes how much? How much time? Can 1 millisecond.
1 millisecond.
Okay? And then this frame, now this frame is actually a signal. This signal will now propagate until it reaches B. How much time does it take? 25 milliseconds. Okay? During that time, what does A do? Well, doesn't do anything. Because this is stop and wait, right? So the window size is 1. I'm sending a frame, and I have to wait. Wait for what? For the acknowledgement. So the acknowledgement will come all the way back. This takes 25 milliseconds. Okay? The transmission time here, as I said, is ignored. Transmission time for the acknowledgement is ignored. This makes sense because the acknowledgement size is very, very small. Okay? So again, during that time, A is doing nothing but waiting. And the can send flag will forbid A from trying to transmit anything else until the acknowledgement is fully received successfully. Okay? Which means that for each frame, time for each frame equals 1 plus 25 plus 25 equals 51 milliseconds. So for total 1,000 frames, we have 51,000 milliseconds. Type. This is that in great life. In ideal life, this is what you're gonna get. But unfortunately, I'm telling you here that 20% of these frames are lost. So the actual number of frames that you are going to send is more than 1,000 or less than 1,000. One more. يعني معناها another 20% of these frames you have to retransmit. So the total time equals the 1,000 frames, okay, multiplied by 1.2, multiplied by the 51 milliseconds. Okay? So that's the total in milliseconds. Or in other words, يعني 51,000 times 1.2. The 1.2 accounts for, the 1 accounts for the original 1,000, and the 0.2 accounts for the extra 20% that you have to retransmit. واضح كده؟
Yeah.
Okay. So we can better nudge it up a little and try to address the same case where now we have go back n and the window size is 7. So this requires a little bit of imagination. We need to know, we need to calculate this. First, let's just look at the timeline for the transmission from A to B. Again, A has these frames waiting to be transmitted. Okay? When we transmit using go back n when the window size is 7, then we are allowed for each 7 frames, for each 7 of these frames, we can send without waiting for acknowledgement. So how does that look like? So the first one will be transmitted. Okay? This is frame, let's say this is frame 0, 1, 2, 3, and so on. Okay? So the first one will be transmitted. This takes 1 millisecond, right?
Yes.
And then, what do?
You put one up.
We don't have to wait.
Put
صح?
one.
We don't have to wait in that case. We can just say, this is frame 1. Where is frame 0? It's next to it here. Is still going in propagation.
Yeah.
So this takes 1 millisecond, and this takes 1 millisecond. Okay? And this is still propagating as a signal. And then we do frame 2, and frame 1 is here, frame 0 is here. And we keep doing that for all the 7 frames. After the 7 frames are finished, then we have to wait. Wait for what? Wait for all of them to go. And then the acknowledgement for them comes back. The acknowledgement is accumulative, right? I don't care about the acknowledgement for this or this or this. I care about the last acknowledgement. Okay? So the last acknowledgement requires to propagate all the way back to A. Which means that the time for one window equals what? The window size is 7, huh? 7 transmission times, right? Plus 1 propagation time plus 1 propagation time for the acknowledgement to come back. So the best way to really imagine this is that, يعني just imagine كده that you are driving a car and you are going into the highway, and in the highway there is a gate. عارف الجيت اللي هي بيدفعوك فلوس دي قبل ما تروح؟ Okay. So the time that you spend to pay is 1 millisecond. This is the service time. Once you pay this the money, then you are in the beginning of the road, in the beginning of the highway, right? Then you propagate back. Okay? Once you are serviced, the next one can be serviced after you. صح? And then all the cars will go as one caravan and they will propagate on that. So imagine if we have only 7 cars. So only the 7 cars will propagate as one unit through the road until they reach to the other side after 5,000 kilometers. ربنا معاك. Okay? So you take whatever time you need to reach to the other end. So it's 1 propagation time for the entire caravan, right? But the service time is sequential. So transmission time is always sequential, always. Propagation time, it depends. How many frames you can send within one window, that's the propagation. So the propagation is only once per window. واضح كده؟ طبعا the acknowledgement also, because the acknowledgement is accumulative, so you may get in between some acknowledgement for frame 0, that's fine. بس اللي يهمني the last one I have to wait for the acknowledgement for the last one, which takes another 25 milliseconds for the acknowledgement to propagate all the way back. ماشي? So also the acknowledgement is once per, the acknowledgement propagation time is also once per window. So this is 57 millisecond per window. So how many windows بقى؟ بالضبط 1000 frames divided by 7. Okay? So the total time is 1000 divided by 7 times 57 milliseconds. Again, this is an ideal world. We multiply by 1.2. Remember, if one frame in the window is lost, I have to go back to the beginning and transfer the whole window, assuming that I did not receive acknowledgement for the previous frames. So the total number is this times 1.2. Okay? Any question or confusion? Okay, so just remember for the case of go back and the propagation time is only once per window. And that's always the case. And for the case of for stop and wait, the window size is anyway 1. So it's 1 propagation per frame. Okay? So that's